These are the notes for AP Calculus on the topic of logistic growth continued. So logistic growth oftentimes is used to measure the growth of different populations. In this case, it says the size of a population of armadillos is modeled by the function p, and it tells you it's a logistic differential equation. Differential because it has a derivative in it. And what we want to do in order to answer all these questions is sketch a graph of what this would look like. But first, we have to get it in the proper form here. So to be able to analyze this, figure out the carrying capacity, we've got to get it to be in this form right here, where this variable here, whether it's p or whatever variable is on the numerator of your derivative there, is isolated in the parentheses, and it is a factored form. So once we do that, then we'll be able to see what the carrying capacity is, this constant right here. Let's see how we can do that for this problem. So here we want to get this isolated as just p. So in order to do that, we've got to factor out a GCF. Not only the 1 over 720, but also the p. So if we factor that out, 1 over 720 p. And then let's see what we're left with. Well, the toughest part is figuring out what's left of this p over 3. The p is gone, we factored that out. But with a 1/3, that's what we had there. So when you factor something out, it's like you're dividing by it. So factoring out 1 over 720 is like dividing by 1 over 720. But that's easier to think about as dividing by a fraction is the same as multiplying by the reciprocal, 720 over 1. And then 3 goes into 72 24 times, add the 0, so this becomes 240. And then minus, now we're just left with the p isolated like we want. Now it fits this form where this is our constant out here times the variable, and then this is the carrying capacity minus the variable isolate. So in this general form for a logistic equation, now we can sketch a graph where the carrying capacity, C, is right there. So let's sketch a graph, and then we can see how we can answer all these questions. So the graph here is not the graph of the derivative, but the graph of the original function that has this derivative. So in this case, p is our variable here. So this is p of t. This is the population of armadillos on this axis. And this is time on this axis. And whatever the carrying capacity is, in this case 240, that's where you're going to have an upper limit where you have a horizontal asymptote there. So there could be a variety of reasons why that is, but there's some upper limit on the population can't exceed that amount, in this case 240. And then if you look at all these problems, it says p of 0 is 45. So that's telling you at time 0 right here, the population is 45. That's giving you the initial amount. That's where it's starting. And then these logistic differential equations always yield a graph that has a similar shape to it. Okay? So they all start off as concave up, and then at some point switches to concave down, and then approaches that horizontal asymptote as time goes off to infinity. And somewhere in here, we've got a point of inflection. Looks to me like mine's about right there. And wherever that is, we know that's going to occur whenever it's half the carrying capacity. Half of the 240 is 120. And you can see from this section here, this part is concave up, shaped like a cup. And then there's our point of inflection where it switches to concave down, shaped like a rock. So this is a couple different things. This is a point of inflection. And it also shows you where it has the steepest slope, where the population is increasing the fastest. So let's take a look at what they're asking for. What is the limit as time approaches infinity of p of t? You can see as time goes off to infinity, it gets closer and closer to this horizontal asymptote of 240. And then it says, for what intervals of p is the graph of p concave up? So we're used to writing intervals usually based on the x, or in this case t values, but we don't know for sure what those values are. What we do know is the intervals of p. And usually these, since we're using the variable p, they usually not be written in interval notation, but instead in equality notation. So you can see it's concave up from 45 to 120. So you can write that as 45 is less than p, which is less than 120. That's the interval where the graph of p is concave up on those p values, those population values. And then for what intervals is the graph of p concave down? Well, you can see it's concave down from 120 to 240. So you say 120 is less than p, which is less than 240. And then it says, for what value p does the graph p have an inflection point? We can see that occurs at p equals 120. So those are some of the questions you could ask. And by looking at the graph, you can easily see all of those, what they would be. All right, let's take a look at one more. So sometimes you have to do a little work to get it to be in that general form for a logistic equation. Sometimes it's already in that form. See how the y is already isolated here? But this one's a little bit different in that it's not, it doesn't have to measure population. I think that's a common thing logistic growth problems will measure. In this case, it says a fake news story spreads through social media at this rate. So we've got y here instead of p, where y is the proportion of the population. In other words, what fraction of the population has heard the fake news story? So that's why you notice in this one the carrying capacity is 1. Because that's like 1 out of 1, that'd be like 100% if everybody, 100% of the population has heard the fake news story. So that's, you can't go beyond that, right? So let me just sketch our graph here. The carrying capacity here is 1. And that's where we'll have a horizontal asymptote. Proportion can't go more than 1 or 100%. And what's different about this one is we don't have a specific initial value to start at. So if that's the case, you can model it with, well, we know it can't be negative, so you can just model it starting at 0 when you sketch your graph. And then it's going to start out concave up, and then again somewhere switch to concave down. And this is going to occur, that point of inflection right at half the carrying capacity. Half of 1 is half. Alright, so what proportion of the population has heard the fake news story when it is spreading the fastest? So spreading the fastest, you can see it's increasing at the greatest rate right here, when it's 1/2 of the population. At the point of inflection, that always occurs there. And for what values of y is the spread of the fake news story increasing at an increasing rate? So the whole graph on this logistic growth is increasing. An increasing rate is another way of saying concave up. Because when something's concave up, the slope is or rate is increasing. So you can see the slope is increasing there, an increasing rate. So that's on the interval. We don't know for sure it's 0, but we just start with 0 because we aren't given an initial value. From 0 to 1/2. So it makes sense that initially nobody's heard the story until it actually is out there. And then what values of y is the spread of the fake news story increasing at a decreasing rate? Well, decreasing rate is another way of saying it's concave down, shaped like the front. Because when it's concave down, you can see the rate or slope is decreasing, even though the overall function is still increasing. So that would occur when y is between 1/2 and 1. And that concludes the notes for AP Calculus on the topic of logistic growth continued.